Decades ago, scientists at the world's largest international laboratories faced this same problem in high-energy physics with experiments of trying to find unknown particles from signals.
The Atlas detectors are capable of recording all of the 600 million collision events per second. Now, if all that data was saved, it would fill up every hard drive on the planet in one day. So a sophisticated trigger system was created to analyze and save in real time 100 of the highest quality collision events out of the millions that happen every second of every minute, of every hour, of every day.
As we've just seen, all the information can't be saved. We can see the problem illustrated here. If a certain amount of time is required to accurately analyze the information, and the information is coming in at a high rate of speed, then much of the information can't be analyzed and is lost because it can't be saved. This all happens in real time. After 17 years of experience working with triggers at CERN in Geneva, Switzerland, in 1991, Crosetto was invited to work at the Superconducting Supercollider GEM experiment in Texas to solve similar problems. While there, he invented the programmable Level 1 trigger, capable of implementing features of Level 2 and accurately finding any particles at very high data input rates. In 1992, Crosetto's 3D flow programmable technology was presented to the scientific community at conferences in France and the United States, where it was compared to other approaches for efficient trigger systems. His innovation was recognized and adopted by the thousands of scientists of the GEM experiment in April 1993. The director of the Superconducting Supercollider and Fermilab requested an international scientific review of Crosetto's project. His project passed later that year. This invention led him to other inventions in particle detection and PET medical imaging. Over the next several years, initially with U.S. funding and later with personal funding and with the support of friends, he was able to build his invention. In 2000, he published several scientific articles and books describing the advantages of his innovations in medical imaging, which he presented at the IEEE Nuclear Science Symposium in Lyon, France. The first demonstration of his hardware was made at the NSSMIC Industrial Exhibition in 2001 in San Diego, California, where he demonstrated the execution of real-time photon detection algorithms. The timing was recorded on a digital oscilloscope. In a 2003 international review, which included Jerry Merriman, the co-inventor of the pocket calculator, Crosetto's innovation was validated for its use in positron emission technology. The panel concluded, Crosetto has done an excellent job of designing the electronics and implementing his ideas, given his limited economical resources. No error or fault could be found for the expected performance. Crosetto has designed and built an industrialized modular system of his invention based on IBM PC boards that allow expansion. The first version performed according to expectations. Each 3D flow board consists of 2,211 components, over 20,000 contact pins connected through only 8 circuit board layers for signals and 6 layers for power and ground. The two major problems we've seen before were, first, if the time allowed to analyze the information was increased, much of the information was never analyzed due to the high data input rate. Second, if the time to analyze the information was decreased, the quality of the analyzed information was compromised. Here you can see the solution and how the information passes through the trigger at a high data input rate, while at the same time allowing the appropriate time to analyze the information. Represented here again by a group of science students is how the trigger works. On the right, the student represents the data input with a brown envelope. As the data comes in, everything is synchronized. The brown envelope, or data, is received and carried to a room for analysis. These students have the appropriate time to accurately analyze the data. As the new set of data arrives, if the room is busy analyzing previous data, the new data is then passed on to the next room to be analyzed, and so on for each room. After the students in the room are finished with their analysis, a white envelope containing the results is then passed on to the student, who then saves only the positive results on the hard drive. In this way, both problems have been solved because no data is lost due to insufficient analysis time. If the time to analyze the information must be increased, or if the rate of data input is increased, then the number of rooms is simply increased to handle the capacity.